Today we have Dr. Masanori Hanada. He is a string theory as well as a scientific advisor to QBraid. I really personally enjoy his lectures. It's very interesting. I'm not very familiar with all the theoretical string theory stuff that he does, but Dr. Hanada does an incredible job of just explaining it, and I think it would be great for the quantum universal education group to just learn about how quantum computers can be also used for uh, essentially a lot of the trying to understand things for theoretical physics as well.
Mhm. So let me screen mode. And because there are not so many participants, you can probably interrupt anytime you want to ask and ask question. Then I can respond. Okay, can I start?
Yes,
Is it
please
okay to
go
start?
ahead.
Yeah, okay. So yeah, so thank you for giving me opportunity to this talk, for this talk. And the title is estimating truncation effect on quantum bosonic systems using sampling algorithms. And it's about a new paper in preparation with these three great collaborators. And this paper itself is rather a technical one, technical improvement of some problem related to quantum computing. But so I don't really think it makes sense to explain detail of this paper itself. However, I think I can use this opportunity to explain why quantum computing is important for physicists. Of course, there are many reasons, but one particular and one of the biggest reasons why physicists have to use a quantum computer. And the keywords are real time versus imaginary time. Real time is usual time, this 2 o'clock, 3 o'clock, this time we are living. And I will explain the meaning of imaginary time and how they are related, what was the difference. And related to that, we will see Hamiltonian time evolution versus Feynman path integral formulation of quantum mechanics. And the important notion is sign problem. And the real time Hamiltonian time evolution leads to sign problem. Then classical computer cannot work. But imaginary time can tell us something about something interesting intuition about physics. And then in that case, using Feynman path integral, we can avoid sign problem. And we can still study various important things on classical computer. Okay. Feynman said that if you want to make a simulation of nature, you'd better make it quantum mechanical. This is very famous phrase. But then first we have to understand, if we can do some computation using classical computer, and if we don't have to use quantum computer, that's just fine. Then what kind of problem requires a quantum computer? We want to make sure we understand that one. Then we have to understand what classical computers can do and what classical computers cannot do, and how classical computer can fail. By only when we understand that point, we can understand why physicists want quantum computer and what kind of problem requires quantum computer. And let's start with the very basics of quantum mechanics. So, we have in classical, we have a coordinate and momentum, x and p. And in quantum mechanics, so they become an operator, x hat and p hat. And those operators do not commute. So commutator, x hat and p hat. So x hat p hat minus p hat x hat somehow takes I times h bar, non-zero value. This is a very weird thing, but this is almost a starting point of quantum mechanics. Classically, we have Hamiltonian, which is the same thing as energy, which is kinetic energy plus potential energy. And it also becomes an operator. And eigenvalue of this operator is energy. And if we solve a Schrödinger equation, then if a Hamiltonian is independent of time, so we have some initial time, and we have an exponential of Hamiltonian acting on this, and that will give us a quantum state at time t, given this Hamiltonian and this initial condition. And this quantum state, there can be various quantum states. For example, we can imagine that one particle is moving along in one dimension. Then we can take a state representing that one particle is sitting at a definite point. Then if we operate x hat on such state, then we get this eigenvalue. So this is a coordinate eigenstate. And this is the state where particle's location is specified. Particle is sitting at point x. We can also take other kind of state, like a momentum eigenstate. So momentum is determined. Okay, so if we act p hat on this state, we get this eigenvalue p. So here momentum is completely specified. Or we can also take eigenstate of Hamiltonian, in which energy of a particle is specified. But the interesting thing about quantum mechanics, which is not bug, which is a feature, is a quantum superposition. So we can take a superposition of coordinate eigenstates, for example. So particle, we don't really know which point particle is localized. Particle is sitting. Of course, if we take coordinate eigenstate, we know that a particle is sitting at that point. But we can take linear combination of them. Then in such a state, we don't really know where particle is sitting until we measure it. Or we can also have a linear combination of momentum eigenstate or linear combination of energy eigenstate. And if we choose a coefficient properly, they can be just the same state. And this is an interesting thing, but Heisenberg's uncertainty principle tells us that this superposition is not just a funny feature. It's inevitable. It's a really fundamental feature of the nature. Okay, why Heisenberg's uncertainty principle says the superposition is inevitable? Usually Heisenberg's uncertainty principle is say that coordinate x and momentum p cannot be determined simultaneously. Precise meaning is that if we have a coordinate eigenstate, this is a superposition of a momentum eigenstate. And this specific coefficient is written like this. Okay, and the momentum eigenstate is a linear combination of coordinate eigenstate. So if we specify coordinate, then this is a linear combination of different momenta. So in that sense, if we specify coordinate, then we cannot determine p. And if we specify p precisely, then we don't know where particle is sitting. So in this way, Heisenberg's uncertainty principle tells us that superposition is an inevitable feature. And here, original Heisenberg's uncertainty principle relates coordinate basis and momentum basis. But of course, something similar is taking place. So if we have energy eigenstate, this is a complicated linear combination of coordinate eigenstate. And it can be also, in general, it's a complicated linear combination of momentum eigenstate. And here in this expression, I imagined only there's just one particle sitting in one dimension. But if we have many particles in three-dimensional space in x, y, z, then we need a coordinate for, then if we take this expression, we need a coordinate x, y, z for first particle, coordinate x2, y2, z2 for second particle, and so on. And the for coordinate basis, we have to specify the location of many particles, right? And so we have this function, which it describes linear combination of many states. Okay, and this function is a function of many variables. And this function makes the physicists' lives very hard. Okay, so is it clear so far? So superposition is inevitable. So we have to deal with this function. If we just take this, we cannot really see, for example, the state where energy is definite. And then imagine that there are n particles moving in three dimensions. Then this function becomes function living in 3n-dimensional space. So real number to the 3n, right? And we would want to handle it on computer. We would want to approximate this with a lattice. So instead of using continuum variable, we want to discretize space. And imagine that so to each of 3n dimensions, we have L lattice points. And two nearest lattice points are separated by this lattice spacing A dig. So this dig means digital. So this continuum value is digitized. And if this A becomes small, and if this A times L becomes large, we can produce this space. Okay, so this is a systematic approximation. And more precisely, for example, if we have just one dimension, we can take this X to be sitting between minus R and plus R. So this point is minus R, this point is plus R. And we take many points, starting with x0 to xl minus 1, starting with minus R plus A, minus R plus 2A, and so on. And by using this K to be the quantum state where particle is sitting at kth point, then this operator x hat can be written this way, using this xk. And momentum square can be written this way, for example. So this is like if momentum becomes a discrete version of momentum, the shift operator, and this is basically shift operator square. Detail is not important, but the important thing is that we can use discrete basis to systematically approximate this continuum space. Okay, so this continuum space can be approximated by using lattice, and we can use finite dimensional truncation of Hilbert space. And after truncation, this so originally there are continuously infinitely many points, but now the number of points becomes L to the 3n. And we have to send this L to infinity to get good approximation. Is it clear so far? If there's any question, I can take. Okay, then let me move on. Then, so now, so there are L to the 3n state, coordinate eigenstate, and it's a linear combination of them. So it's an L to the 3n component vector. And Hamiltonian becomes L to the 3n times L to the 3n matrix. And the good approximation is achieved when this L is sufficiently large, right? And in when L is 2, this is analogous to qubit of fermion. But in like a bosonic particle living in this R, so we have to take this L much bigger and use a qubit to approximate this many points. And here comes the problem. So on classical computer, these many numbers are stored and manipulated separately, because a classical computer cannot directly handle linear superposition of many states. But then, imagine that there are 10 particles. It's a very small system, right? If we imagine molecules in moving in this room, we need really, really many, order of 10 to the 23 particles. But even when n is 10, then this dimension becomes huge. So if we just use 2 points to each direction, which is admittedly very not good approximation at all, we already have this many numbers. And if we have 5 points to each direction, then this is already a huge number, which cannot be handled on classical computer. So classical computer cannot even handle 10 molecules moving in the room. And the reason is this big power, which is required to approximate Hilbert space. And this is inevitable because we have to deal with superposition. So if we use a coordinate basis, which is a very easy thing to handle theoretically, the energy eigenstate has to be linear combination of so many states. And this is the reason. So if classical computer can handle this big number, large degrees of freedom, then there was no problem. But we don't know how to do. That's a problem. On the other hand, on quantum computer, these numbers are stored and manipulated simultaneously as just a single quantum state. And this L to the 3n, so this Hilbert space can be mapped to a set of qubits. And then if we have n qubit, we can describe n2 to the n qubit different quantum states, a linear combination of this many states. So by using by taking n qubit, so such that the 2 to the n qubit becomes L to the 3n, we can describe this system on quantum computer. And if we have a quantum computer, there's nothing difficult. We don't really have this exponential increase of cost. So this is the reason the quantum computer is better for such problem. So in classical computer, it's difficult to handle the Hilbert space. So for example, this simple real-time evolution, time evolution following a Schrödinger equation is already very hard. But still, actually, classical computers are good at certain tasks. So classical computer cannot handle this, but classical computer can handle different kind of problem. And you may not know what this expression means, so I will explain. And this is related to thermodynamics, or more precisely, thermodynamics in an equilibrium situation. So Boltzmann was a famous Austrian physicist who was a kind of founder of statistical mechanics. And if you go to Vienna, there is a nice physics institute called Erwin Schrödinger Institute. And Erwin Schrödinger Institute is facing to Boltzmann Street. And very close to Schrödinger Institute, you can find Hotel Boltzmann. So if you go there, you can stay at the Hotel Boltzmann and work in Schrödinger Institute. That's very nice thing. And according to Boltzmann, Boltzmann didn't know quantum mechanics, but his statistical mechanics can be generalized to quantum theory. And according to him, state with energy, definite energy, such microstate appears with the probability proportional to exponential minus energy over temperature. So we can imagine various state, different microscopic state, which looks almost the same macroscopically. But the probability of such a state is which state realized in this room, for example, is proportional to this factor. So when temperature is fixed, high energy state is less likely. I mean, for each state. Okay, and this g of t, which is called a partition function, is normalization factor appearing here. Okay, and in terms of quantum Hilbert space, this is trace of exponential minus h hat over t. And if you want to do thermodynamics, you create quantum state E with this probability and take average. This is the prescription of quantum statistical physics. And actually, classical computer can handle it by using so-called Feynman's path integral and Monte Carlo simulation. Feynman said we should use a quantum computer to study nature, but actually he also provided us with a nice method to study some part of nature using classical computer. But that does not work for all kinds of interesting problems. So kind of problem to which this method doesn't apply, he suggested that we should build a quantum computer. Is it clear so far? I will explain this Feynman path integral, starting with the next slide. Okay, let me move on. So classical computer, as we will see, I will explain why this is the case, but classical computer cannot really handle this real-time evolution. This t is real number, and this is user time. But this, if you imagine that this t, imagine this, replace this t to minus I times h bar over temperature. This is imaginary number. But if you replace, this factor becomes this. In this sense, this is called the imaginary time convention. And of course, there is a more precise argument how this kind of calculation is related to this kind of calculation. But in short, usual time evolution is real-time evolution. And the thermodynamics can be studied by using imaginary time evolution. And the classical computer can often handle imaginary time evolution. And so as long as we study imaginary time, we can use a classical computer very often. Okay, and the quantum computer, I say the quantum computer can handle this, but the quantum computer with error correction and with many qubits can handle this. But imagine we want to use a NISQ device to do some interesting study, some interesting physics problems. But this device may not be good enough to do this precisely. Perhaps this device can be used, but maybe there are too many gates for this, too many big error for this. Maybe NISC device can be used to simpler only for simpler problems like DQE, for example. And we don't really have many qubits, so maybe we cannot go to very large L. L is the number of lattice point, which is needed for good approximation. And because NISC device cannot correct the errors, maybe we have, without knowing some precise answer, maybe we don't really know if the simulation result we obtained from NISC device is correct result or not. So if we can do some cross-check with the classical simulation, it would be really good at the NISC error, I think. So I want to think what can be done for cross-checking or benchmarking the result from NISC device by using classical computer. And specifically, the problem we will focus on is I said that this L, number of lattice point, has to be large, but how large L is needed to control truncation effect? This is a problem I want to think about. Is it clear so far? If there's any question, there's any question so far, I can take. Is it okay to move on? Yeah. By the way, I cannot see chat window. It's in full screen. So yeah, thank you. So I will then move on. Okay. So I say that Feynman's path integral plus Monte Carlo simulation can be used to study thermodynamics in imaginary time formulation. And we want to do something similar to estimate the truncation effect to see, for example, how many qubits are needed to precisely study physics. Or if on NISC device we can use only small number of L, then what should be the result we expect with such truncation error? I want to introduce a technique to study such problem using classical computer. But to do that, before doing that, let's see what Feynman actually did. What is Feynman's path integral, and how that can be combined with the Monte Carlo simulation? I think this is more, it contains more information useful for your research in quantum physics, I think. So let's see what Feynman did. So in classical mechanics, there is a Hamiltonian formulation and a Lagrange formulation, and they are equivalent. But depending on the problem you want to study, sometimes Hamiltonian formulation is useful, sometimes Lagrangian formulation is useful. And quantum mechanics originally built by these people, plus many more people. This is Hamiltonian formulation. Because you have a Hamiltonian expressed as operator, and you act that operator to a quantum state, and then how time evolution is described, right? So here Hamiltonian is manifestly used. And Feynman's path integral is actually a counterpart of Lagrange formulation. And they are equivalent. So let's consider real-time version first. Okay, Feynman's argument can be used for real-time and for imaginary time. Both cases it can be used, and the original work is for imaginary time. And imagine that as an initial condition, that particle is sitting at point xi. This I is initial. And you act Hamiltonian on this, and then perform a measurement for the location at the final time. And this xf is a location at the final location of the particle. And if you take a square of this amplitude, you can get the probability that the particle will move from xi to xf, right? Let's calculate this. Okay, so this is, of course, we know how to calculate it using a Hamiltonian formulation, original formulation of quantum mechanics. Okay, so this is time evolution, but then let's divide this time to be many intervals and insert identity here. Essentially, I'm not doing anything because multiplying one doesn't do anything. And if you multiply this and this and this and this, we get this. Okay. This is just a trivial. And then I insert this, use this relation in many places. So this one becomes this x1 ket times x1 bra integrated over x1. And this one becomes xk minus 1 bra xk minus 1 ket xk minus 1 bra integrated over this. Is it clear? This is just replace all these ones with this. And so x1, x2, x3 are like a location, can be regarded as the location of particles at the time delta t, 2 delta t, 3 delta t, and so on. Okay, and the point here is we have to integrate over these intermediate steps. And let's say this small piece of this, okay? So I wrote xl to be x at time tl. Okay, they are the same thing. And then if this delta t is small, this exponential, this h hat is v times half of p squared. This can be written like this, up to small correction. And we insert 1 between here, okay? And similar to this, we can insert momentum eigenstate. So p ket p bra integrated over p. We can do the same thing. And then this one acting on this just gives a number. This one, this p hat acting on p just returns p. And p and x, this inner product is exponential minus ipx. So we get this. And we integrate over p, this because this is Gaussian integral, and we get this. And this piece is actually Lagrangian at time t l plus 1. This way, we can relate the Hamiltonian to Lagrangian. And each piece becomes Lagrangian at each time. So what this, in the end, is related to some path integral. So we have exponential of I times integral of Lagrangian. Integral appears because we take a sum of this, okay? And this in the limit where this dt is small, this becomes integral. And we have integral over these intermediate locations. So we have to consider any possible path or possible path, and corresponding to each path, we have a Lagrangian corresponding to that path, and we take a sum over all integral, all paths. And we impose boundary conditions such that initial location is xi, final location is xf. But other than that, we consider all possible paths connecting these 2 points, and then take sum. And then we get this. This is Feynman's path integral. And this is a beautiful relation, but you may wonder, why it's useful. But actually, it's very useful for various purposes. And particularly, I will show how it's useful for thermodynamics. Okay. And so originally, Feynman rewrote this real-time evolution following a Hamiltonian time evolution, this kind of path integral. So weight is given by exponential of Lagrangian, and you take all possible paths connecting initial point and the final point. And if we repeat the same thing for imaginary time, so this it changes to slightly different thing, which I will explain shortly. And the time between the initial point and the final point is actually 1 over temperature. And instead of, and here for thermodynamics, we don't really specify the initial location. Because of this trace, actually, what we impose is initial point and final point are the same point. But other than that, we should consider all possible paths. So all possible cyclic paths in this imaginary time evolution should be summed over. This is a Feynman path integral for thermal theory. And this can be handled by using classical computer if we use Monte Carlo simulation. And Monte Carlo is a name of rich people's neighborhood in Monaco, famous for Formula One Grand Prix, where Ayrton Senna had, many legendary races, and casinos, and the rich people live there. And it's famous for gambling. And is a kind of Monte Carlo simulation is a kind of simulation which uses random number to do some sort of integral. And in actually, people like von Neumann or Ulam came up with such idea during Manhattan Project. And the Manhattan Project is a project for making atomic bomb during World War II. And of course, they didn't want Germans or Japanese or Italian to know such a technique. So it was classified information, and they needed to give a code name for that. And then the Greek guy called Metropolis came up with the idea of Monte Carlo, because using random number sounds like a gamble. And one of Ulam's relative was crazy for gambling, and that guy even tried to borrow money from Ulam to go to Monte Carlo. So there is that kind of background story, and they thought that, okay, using Monte Carlo for this technique can be fun. So they gave the name of Monte Carlo. In retrospect, it could be Las Vegas simulation, but during World War II, actually Las Vegas wasn't a big gambling city yet. So that's the reason it became a Monte Carlo simulation. Anyway, that's not really important information. But anyways, so for imaginary time version, we can do the same thing. Okay, so here we don't have I. Other than that, everything is the same. And we get this probability at each pass x. And the important thing here is this is a real and a positive number. And it literally means the probability of each path x appears according to Feynman's interpretation. And the Monte Carlo simulation, or more specifically Markov chain Monte Carlo simulation, which is called MCMC, generates ensemble of all those paths with this probability. So if you have many different, so you can generate many paths using a certain algorithm. And I don't really have time to explain the details, so I just refer you to a book I wrote recently with Matsura. And I think if you have university affiliations, you have a good chance that you can freely download this by university library. Okay, and here their detail of the Monte Carlo simulation is explained. And anyway, so those paths are generated with a relative probability proportional to this. And if you just take an average of many samples, you can get the expectation value. And the important thing here is that some path has a bigger probability. Some path doesn't have a small, bigger probability. Or more precisely, if you have like a low energy state contributing to low energy physics, like a ground state. Ground state, very roughly speaking, ground state corresponds to some path with a bigger probability. Higher excited state most corresponds to path which has a smaller probability. And in Monte Carlo simulation, most of the computational resources are devoted to create important samples which has a bigger probability. So somehow, it may not be very precise, but intuitively, what the Monte Carlo simulation allows us to do is that we can select a subspace of a Hilbert space where close to low energy modes. And so sort of truncation is done by using this algorithm. Okay, so we can somehow cut out the unimportant part of a Hilbert space. And so that's the reason even a classical computer, we can handle this. But in the case of real-time evolution, we had I here. So this is a complex number. So this is not really probability, but because probability has to be non-negative, real number, and it must be 0 or larger. And so we cannot use Monte Carlo simulation. So this is complex number, sometimes negative. So we cannot use Monte Carlo simulation. So it's called the negative sign problem. As long as negative sign problem doesn't exist, we could use Monte Carlo simulation. But for Hamiltonian time evolution, we cannot use it because of this sign problem. Still, we can use Monte Carlo simulation for thermal physics. And Monte Carlo doesn't work because of this I. And also in other places, if we take an analytic approach, for example, because of this I, computation becomes harder compared to this situation. So this I is really problematic guy. So one very respectable physicist from Stanford once told me that he hated this I. But actually this I, so I in Japanese means love, and nothing can be more important. So we have to accept this, we have to live with this I. So that's the reason, we have to deal with this important I, factor I, and that's the reason we desperately need quantum computer. Okay, we have to set this I. Is it clear so far? I try to explain why physicists, and especially Japanese physicists, need a quantum computer. Okay, let's go let's move on to path integral with truncation. So let's just repeat the same computation, okay, with imaginary time, which appears in thermal calculation. So we had the location of a particle at the time TL, and this TL plus 1 is TL plus delta T, okay? And I want to see this amplitude. And assuming this delta T is small, I just split this to two pieces, okay? And I insert 1 between here, and this one is this integrated over this. And then this x hat acting on this x just gives this number. And this p hat acting on this p just gives this number. And we can use this again. And we can integrate this p, and we get the L tilde. So this L tilde was actually this which is just energy. But here, this was a Feynman's argument. And it assumed that this x is continuous, and the p is continuous. And now we want to make this x discrete, because we want to discretize it to put in a quantum computer. Then these steps fail. Okay, so Feynman's argument cannot be used after this point. However, still we can, so this point is fine. And then we could just, this acting on this is just a number. And actually we can just treat this piece without going to final form obtained by Feynman. Just expand this way, which is good precise, which becomes precise when this delta T becomes infinitely small. And we can easily see that this part is actually non-negative for any xtl and xtl plus 1. And if this is non-negative, then we can just use Monte Carlo simulation. So it's not very as beautiful as Feynman's path integral. And expressions looks a bit messier, but still we can numerically handle it. So to see this, let's see the explicit form of this, okay, or explicit form of this operator in coordinate basis. So p hat the square for single particle was written like this. Okay, and if we have n particles, each of them have this kind of expression. So instead of just one number representing one coordinate, we need n numbers. Okay, and this part just becomes like this. And here, corresponding to this part, like we have a sum of all particles, and for each particle, ki is shifted just by 1. Okay, but only one of k is shifted. This is important thing. And then this combination, which is appearing here, this expression was just for one particle, but for multi-particle, we need the sum over p squared for particles. But then, just by plugging this, you get this identity times something plus something, and these are the coefficients. And these coefficients are all positive. This is positive by definition. This is positive by definition. And this is positive if this delta t is sufficiently small. And then if all these coefficients are positive, we can simply use a Monte Carlo simulation because this expression is just positive. So this just becomes a sum of a positive weight. That's it. And so, so what we did this time is, just this observation and just did the Monte Carlo simulation. So uh, it looks almost trivial. But the story behind it is, related to physicists' long struggle to cut out what can be done, cut out a sector of interesting physics, which can be handled on classical computer. Okay, and our modest contribution here is that actually this kind of argument, which was known more than 50 years, can actually be generalized in a discretized setup. And that will allow us to study truncation effect of a boson, which is really needed to understand the quantum simulation. And let's see how the truncation effect can be estimated. Okay, so imagine that the energy, so there are n bosonic variables, and this energy eigenstate is a linear combination of this coordinate ideal state. Okay, and this x was originally Rn, but we want to discretize it on lattice, so like this. And what people expected for a long time was that if we look at the low energy physics, low energy observable, like low lying energy eigenvalue, digitization effect. So if this a digit times L is taken sufficiently large, and if wave function is localized around here, then we can focus on this a correction associated with the finite value of a digital, and then discretization effect should scale like exponential minus 1 over this a digit. So if this lattice becomes finer, this correction to true value in original theory should decay exponentially. And like if we also have other observable which capture low energy physics, then correction to true value for continuous x should be exponentially suppressed. And I think it's widely believed and checked for small number of n, but it was hard to go to larger n. And the problem associated to that is that, okay, so even if this is correct for large n, practically how small value we should get. What is optimal value where cost of the quantum simulation is not too big, but the approximation isn't too bad. For that, actual explicit computation is needed. But because of the quick growth of dimension of Hilbert space, people couldn't really do it. And what we say is that actually we can do it just using Monte Carlo simulation, using the method I explained. And as an example, we studied the lattice regularized two-dimensional scalar QFT on 4x4 lattice. So I don't really show the detail of the this theory, but this is a very fundamental theory. The simplest kind of so-called quantum field theory, which is important in many physics problems. And for example, in a famous paper by Jordan, Lee, and Prescale, they considered V theory and explained how quantum field theory can be studied on quantum computer. And we have to take infinite times infinite lattice eventually, but already 4x4 lattice, which is very close approximation of quantum field theory we want to study, this also estimate was very hard. But we can easily do it by using laptop in our case, if we use this Monte Carlo method. So if we have 4x4 lattice, at each lattice point, one bosonic degree of freedom is living. And we study the system of 16 bosonic degrees of freedom, which was out of reach before. And we just use this method. And then here we studied some specific limit where we know the exact answer when digitization is removed. And then we studied how big a correction appears on top of that exact value. And then we could see that this direction is 1 over a digital. and this direction is deviation from exact value, and we can see exponential decay here. And actually here, if you look at this expression, we had delta t, and we have to send this delta t to 0 in order to get a precise result at each fixed digitization age. And we used the finite value of dt, so there is some error. And in our specific setup, we expect a few percent error. But above this point, we can see that the digitization effect is exponentially decreasing. And it seems that in this specific case, if we take use 3 qubits for each bosonic degrees of freedom, so that 8 degrees of freedom, 8-point lattice can be used for each direction, error is actually pretty small. So so the question was how large L was needed, how many qubits are needed to study bosonic system. If it was fermion or qubit, just 1 qubit was fine. But even for bosons, it seems that a few qubits is already good enough, and which is very promising. So previously, for such resource estimate was really hard, and even using the supercomputer, you couldn't go to like a 10 qubit. But now using this lattice Monte Carlo method, you can just use your laptop to estimate truncation error, and you can make a quantitative resource estimate for quantum simulation. And I think we can use this to benchmarking NISQ simulations. And I didn't explain, but this method may not work with fermion or with the other truncation scheme. By truncation scheme, I mean here we had the coordinate basis and made the coordinate discrete. But instead, we could make a momentum discrete, for example, or we could use something like harmonic oscillator basis, and just keep lower mode and then truncate the higher excited mode in harmonic oscillator basis. Such truncation may lead to sign problem in our case. So I'm not really sure to which truncation scheme we can use this kind of method. But at least for coordinate truncation, it works. Anyways, I think so we should understand what can be done on classical computer, what really requires quantum computer. And the combination of classical and quantum devices should lead us to exciting research outcomes, I think. Thank you very much. This is my last slide.
Thank you.
Maybe it was a bit too technical.
Does anyone have any questions? Probably, maybe not.
No, I think we don't have any questions.
I thought it was great. I think this is very cool to think about how you can approximate the Feynman path integral and then try and use quantum computers or not. This is very.
Yeah. That simulation itself, people by using that method, it's used in condensed matter physics, high energy physics, and many things studied. But people are frustrated because many interesting things. So I said it's equilibrium thermodynamics. So it's kind of static physics. You cannot see how things dynamically change with time. And as long as we study static physics, classical computer is very powerful. But as soon as we try to go to time-dependent physics, suddenly things become super complicated. And that's one of the biggest reasons why physicists want to see it. Because what we can do in the experiment, many interesting things are time-dependent. And this sign problem seems to be very at first sight, it looks almost a stupid program, and maybe you think just by some technical improvement you can avoid it. But actually, there is a paper which claims that if you can solve this sign problem in a generic way, such that Monte Carlo simulation can be used for any theory with this sign problem. That implies P equals LP. So it looks almost a stupid, technical issue. But actually, if you can solve it, it claims P equals to NP. So it must be very deep question. So yeah. And that the quantum computer can handle it does not mean P equals to NP. But if you solve this sign problem on classical device using, if you can find a solution, P is NP, and it's highly unlikely that such statement is true.
I think we have one question here from Chiwei where they are asking if there's a paper linked on this subject, which I think will be released soon. Is that correct?
Yes, and we are hoping that we can submit this during this week, hopefully on Thursday. So maybe I can send you once it appears. I can send it to you, and then maybe you can send with the audience.
Sounds good.
And I think this this talk itself is kind of technical, but this idea of cutting out problem which can be handled by classical computer, this is really important thing because we do have good classical computer. So yeah, learning about the Monte Carlo simulation can be very useful. I think Monte Carlo simulation is used in various places. It can be really a good practical tool for you, even without even waiting this. Just from tomorrow, you can use it for many problems. And you can identify something truly difficult and require quantum computer.
All right, I think that's all for today's talk.
Okay, then thank you very much, and I will send you the slide over Slack.
Thank
Thank you so
you.
much.